All right, folks, let's move on with, we're going to finish off section 1.4, continuity and one-sided limits, part 2. Moving on to page 2. A couple of examples. These are going to involve the intermediate value theorem. As a refresher, I'm going to just quickly jot down the intermediate value theorem for us. So, intermediate value theorem, remember we abbreviate that IVT. IVT tells us that if a function is continuous on a closed interval, then the function has outputs between the endpoints of the interval. So it will take on all values between the endpoints of the interval. All right, so let's go ahead and see how we might use intermediate value theorem in some examples. So example 1 here says, verify that the intermediate value theorem applies on the indicated interval and find the value of c guaranteed by the theorem. So we have a function, it's a quadratic function, f of x equals x squared minus 6x plus 8, and the interval we're looking at is the closed interval from 0 to 3, and we want to find the 0 that is on that interval. So let's go through this step by step. So f of x is a polynomial. That tells us that f is continuous on the interval we're interested in. How do we know that? Because polynomials are continuous on the real number line. Okay, so next step, I'm going to look at the value of the function at the left endpoint. F of 0 is 8. Plug in 0 for x, and we get positive 8 as the output. Also going to look at f of 3. That's going to be 3 squared minus 6 times 3 plus 8. And that value is negative 1. So let's look at what we have here. For our left hand point, f of 0 is greater than 0. And for our right end point, f of 3 is less than 0. So now we can say, by the intermediate value theorem, there must be at least one value on the interval from 0 to 3 such that f of c equals 0. So there's got to be at least one value on that interval from 0 to 3 where the output of the function is 0. And that's because at the left end point, the output is greater than 0. At the right end point, the output is less than 0. Because the function's continuous, it must go through 0 at some point. So now let's find that value of c. We're going to plug c into the function. So I'm going to have c squared minus 6 plus 8. Well, that is a pretty easy polynomial to factor. That's going to be c minus 4 and c minus 2. So that gives us values of c equals 4 or 2. So the values of c equals 4 or c equal 2 will give me an output of 0 for that function. Well, guess what? We're not asked for both of those. We're only asked for the value on the interval from 0 to 3. So we're only going to report the value of 2. Okay, that's an example of using the intermediate value theorem. Let's look at one that's a bit more challenging. Here we're going to use the intermediate value theorem to show that this equation, it's not a function, it's an equation. I have e to the x equals 2 times cosine of x has at least one positive solution. We're going to try to do it without actually graphing the two functions to see where they intersect. So first thing I'll mention here, both sides of this equation, both functions are continuous for all real numbers. And why is that important? Because in order for us to use the intermediate value theorem, we have to have continuous functions. E to the x is an exponential. 2 cosine x is a trigonometric function, and we know that those are continuous for all real numbers. Okay, so let's jump back down here and start to piece this together. I'm now going to define a function. I'm going to let f of x equal e to the x minus 2 cosine of x. So let's talk about this function for just a second. Basically, I'm taking the equation that I was given and I'm creating a function. If the output of this function equals 0, that means e to the x and 2 cosine x are equal. So when the output of this function is 0, I have a solution to the equation that I was originally given. So that states in words what I just said. X equals c is a solution to that original equation if f of c equals 0. Okay, so now what do we need to do? We need to check this function on an interval, and I have no idea what interval to choose. I just know that the problem says at least one positive solution. So I'm going to pick an interval that's positive, but not too big. So let's look at the interval. We'll start with from 0 to 1. Now I know what you might be thinking to yourself. 0 is not a positive number. It's neither positive nor negative. That's okay. We're going to choose that as our left endpoint just to help us have a place to start. So if we check the function on this interval, we're going to look to see what the output of the function is at both of those endpoints. F of 0 is going to be e to the 0 minus 2 times the cosine of 0. And let's think about that. E to the 0 is 1. That's a 0, by the way. E to the 0 is 1. And the cosine of 0 is 1. So this is 1 minus 2. That gives me an output of negative 1. So I'm going to make the following statement. F of 0 is less than 0. So now let's check that function at the right endpoint. F of 1 is going to be e to the 1 minus 2 times the cosine of 1. And remember, we're working in radians here. Unless specified otherwise, we're always going to be using angles that are in radians. So this is something I need my calculator to evaluate. And when I plug that into my calculator, let's be specific here. It's not going to be exactly equal to. It's going to be approximately equal to 1.638. So and again, I evaluated that with my calculator. So now I know this. F of 1 is definitely greater than 0. I mean, clearly 1.638 is greater than 0. Okay, so I'm practically done now. I just have to make a final statement here. I have all that I need. By the intermediate value theorem, f of x has a 0 on the closed interval from 0 to 1. Therefore, e to the x, oh folks, that you deserve better than that. That e is terrible. Let's start that over. Oh, that's much better. E to the x equals 2 times cosine of x has at least one solution on the interval from 0 to 1. And this solution, or solutions, is positive. All right, folks, that's a pretty cool example involving the intermediate value theorem. All right, one last quick comment here. How do we know that the solution is positive? Well, the only interval of values that we're looking at here, they're all positive values except for that left endpoint. And when I plugged in that left endpoint, I got an output of the function that was less than 0. So I know that the solution is going to be to the right of 0 and to the left of 1. So it's going to be all the numbers that are on that interval to the right of 0 and left and 1 are positive. Notice here also that I said at least one solution. Okay, at least one solution. There could be more. And again, the intermediate value theorem is an existence theorem. It shows us that the value of interest exists. It doesn't tell us exactly where. It also doesn't tell us how many. We just know that there's at least one of them. All right, that's enough for those two examples. Let's jump down here into... Folks, you might want to pause this, maybe take a break, get yourself a cup of coffee or something, because this next example is really, really exciting. This next example is actually a real live AP question. This is from the 2016 AP Calculus AB examination, and this is free response question number 1, part D. You might be wondering what happened to parts A, B, and C. Well, we don't have enough calculus yet to do those, so we're just going to do part D because it's really relevant to what we're working on now. All right, we'll start just by reading the problem. Water is pumped into a tank at a rate modeled by W of t equals 2,000 times e to the negative t squared over 20. and that's in liters per hour, and we're given the time interval from 0 to 8, where t is measured in hours. So they've given us a function for water being pumped into a tank. Water is then removed from the tank at a rate modeled by R of t, liters per hour, where R is differentiable and decreasing on the interval from 0 to 8. Notice that's the same interval we were given up here for W of t. Selected values of R of t are shown in the table above. So we don't actually know the exact function for R of t. We're just given a table of values to represent R at 1, 2, 3, 4, 5 different times. At time t equals 0, there are 50,000 liters of water in the tank. So they give us an initial quantity. First thing we need to do is talk about this word right here, differentiable. You have no idea what that term means. So I'd like to make a note about it. Okay, we're soon going to learn that the term differentiable also implies that the function is continuous. So we can state that the function R of t is continuous on the interval in question from 0 to 8. Okay, so let's just kind of stop, gather our thoughts, and see what's going on here. We have a tank. And coming out of that tank, we have water at a rate R of t, and that's in liters per hour. We also have water going into the tank at the rate of W of t. So that's water. Oh, hold on. Water should be blue, so we got water going in the tank at that rate, and then coming out of the tank at the rate R of t. Okay, so how on earth are we going to do this problem? Well, we haven't even read the question yet. All we did was kind of read the problem and then draw pictures. So let's read the question now. For the time interval from 0 to 8, is there a time t when the rate at which water is pumped into the tank is the same as the rate at which water is removed from the tank? Explain why or why not. So this is really a yes or no question. Yes, we can say there's a rate in which there's a time in which the two rates are equal, or no, there is not. So it's a yes or no question, but I guarantee you, if that's all you put on your paper, you're going to get no points for it. So we need to construct a solid argument here as to why we think the answer is yes or no. So here's how we're going to do that. So I'm going to let n of t, I'm going to define a new function, and that's kind of my net function. That's the rate in minus the rate out. So we now have this function n of t, which is the net rate of change of water in the tank. It's the rate of change in minus the rate of change out. Make a quick statement here. If this function n of t is equal to 0, then the rate in is the same as the rate out. And that's what we're trying to find out. Is there a time on the interval when the rate in is the same as the rate out? So if n of t equals 0, we can say yes, we do have a time when the rate in is equal to the rate out. Okay, so let's talk about the continuity of n of t. N of t is a continuous function on the interval from 0 to 8. Well, how on earth can I make that statement? Well, both of the components of that function, w of t is an exponential function, it's continuous on the real number line, and r of t, which is differentiable, and we already talked about what that means to us. It implies continuity. So w of t and r of t are continuous. Okay, so let's move on. Let's check our endpoints. Let's evaluate the function at the left endpoint of 0. Well, it's going to be w of 0, which is going to be 2,000 e to the negative t squared over 2. That's 2,000 to the 0 minus r of 0, which is given to us in the table as 1,340 liters per hour. So let's just make a note of that. N of 0 is greater than 0. Now let's look at the right endpoint. Let's look at the net rate of change when t equals 8. So that's my W of t, 2,000 raised to the negative, it's going to be negative 64 over 20 power. And then I'm subtracting R of t at t equals 8, which is 700. And that I'm going to evaluate on a calculator, and I get a value that's about negative 618 liters per hour. So clearly, the net rate of change at the right endpoint is less than 0. Okay, so what do I have here as a final conclusion? Well, I have my left endpoint, 660 liters per hour. That's greater than 0, which is greater than my right endpoint, negative 618 liters per hour. So, by the intermediate value theorem, there is a time on the interval from 0 to 8 such that the rate in equals the rate out. So that's it, folks. That's a pretty cool example. I love that example because it's really a one-word answer. The answer is yes, but it requires a whole lot of mathematics to answer that question thoroughly. So just give you a last note here before I sign off for this video. This was a question on the AP exam during the first year that I taught AP Calculus. And it's one that when the questions were released and I looked at this one, I'm like, oh man, IVT, we covered that so early in the year. I really hope my students remembered the subtleties of that theorem. Well, we're going to see IVT again and again because I want it to be something that you can be successful on when we come to the AP test in May. So again, this is a real live AP question involving the intermediate value theorem, and we will see more throughout the year.